All right, welcome everyone to HelioHub's Summer 2025 Solar Circuit. As you know, every Tuesday this summer we're doing certain presentations on topics related to heliophysics. And today is July 8th, and we have a mission highlight, a Helio mission highlight, and it was student pick. We polled a number of the students on our HelioHub Discord, and overwhelmingly we had a clear winner. And if I can click here, just to remind everybody that HelioHub is sponsored by the NASA Drive Science Centers. If you want, and coffees in particular, if you want more information, just go to science.nasa.gov/heliophysics/DSC for Drive Science Centers. All right, the heliophysics mission's student choice, overwhelmingly NASA's HelioSwarm, with the tagline I've been seeing lately, the nature of turbulence in space plasmas. And I know you're going to hear more about that today from our very special guest from the HelioSwarm mission, Dr. Christopher Klein. We'll be introducing him in a moment, but I want to just give everyone a quick little overview of NASA mission life cycles, because that's very important here, because this mission has yet to get to launch phase. So a typical NASA mission goes through various phases. They are phases A through F, with phase A kind of just being identifying the need for a particular mission. And then you'll eventually, hopefully, get to the all-important phase E, which is actually the operation of the mission after launch. And then many missions actually keep going on and on in phase E. But eventually they reach the end of their life and get to phase F, decommission. All right, with that, I'm going to turn it over to Claudia, and you're going to introduce our special guest for HelioSwarm today.
Yes, I'm excited to introduce Dr. Christopher Klein, an associate professor at the Lunar and Planetary Laboratory at the University of Arizona. He earned his PhD from the University of Iowa in 2013 and specializes in solar and heliospheric physics with a focus on turbulent plasma dynamics and the solar wind. Dr. Klein is a co-developer of the Arbitrary Linear Plasma Solver ALPS, a tool used to study non-equilibrium plasma systems. His work combines large-scale numerical simulations with in situ spacecraft observations from missions like NASA's Parco Solar Probe and the upcoming HelioSwarm. Through this research, he aims to uncover the fundamental mechanisms that govern energy transport in space plasmas. Please welcome me in welcoming Dr. Christopher Klein.
Thank you very much for that introduction. My desktop just broke down, so can you all hear me on this laptop?
Yeah, can hear you.
Excellent. Great. Well, let's ignore the technical difficulties and go ahead and get started. So as there we go. Let's hide that Zoom screen so I can see what you're seeing. And so I will be talking over the next 40 or so minutes about HelioSwarm, or a mission that we will be hopefully launching by the end of this decade to better understand the nature of turbulence in space plasmas. Any mission is not just a single person's effort, and so we have a very vast science team going all the way from Alexandrova and Arzamovsky to Zank and Zweibel, covering a variety of different theorists and observational specialists. The PI of this mission is Harlan Spence, who's at the University of New Hampshire. And we have instruments that are being built both in the US and from international contributors over in both the UK and in France. I do want to encourage any of you, if you have questions, please don't hesitate to interject at any point. I'm happy to discuss any of the elements here in whatever depth you'd like. But to start off with, what fundamentally is turbulence? What is this thing we're trying to understand? If we have to put it in a single phrase, I would say turbulence is multi-scale disorder. It's a collection of statistical nonlinear fluctuations that are statistically can be described as a function in terms of multi-scale processes. Effectively, you can think of it in your, I don't know, coffee cup, appropriate to this group, where you put creamer in at the beginning to sweeten it up a little bit, and you stir, right, forming those nice vortices. Those vortices will start to break up, shear one another, and go to smaller and smaller scales. We want to understand how that energy moves to those smaller scales, how those eddies, those little whirls of creamer in your coffee, shear one another apart, and eventually how energy is removed from that system. A turbulent theorist will not necessarily look at that spatial plot, which was from this massive, I think they labeled it in the paper as the world's largest three-dimensional MHD simulation, but they'll think about it in terms of other representations, right? That kind of eddy picture that I was talking to you about of energy being injected, these large swirls that are the size of your coffee cup, breaking up into smaller and smaller swirls. Well, you can describe the spatial structure of each of those swirls, right? The length scale of this eddy right here, and represent that in terms of a spatial scale. Frequently, we like to think of it in terms of an inverse scale, so a wave number 1 over the spatial scale rather than the spatial scale itself. And one can, and typically does, work through some kind of power law description to get something that you may have heard of, a Kolmogorov spectrum, where you get this power law distribution saying that at very large scales you have more power than at smaller scales, and there's a specific distribution of power. That's something that enables us to understand how energy, mass, and momentum is transported within, distributed throughout, and then eventually removed from these systems, right? We know that energy is being injected in at these large scales, but we want to understand what's happening when we break from that power law distribution. When we see a changeover and energy starts to be removed. We want to understand what physical processes are arising there. Now, importantly, this is not just a fluid system. If it were, life would be somewhat simpler. But in addition to those neutral fluids, we also have the fact that you have charged particles that are self-consistently creating and then responding to electromagnetic fields. Just as a show of hands, how many people here have seen the MHD equations before? Okay, so either you're all have not. Okay, great, Phoebe, thank you very much. So effectively, instead of having just a description of the evolution of the fluid flow, this du dt right here, that only depends on the thermal pressure, the presence of the magnetic field changes how the fluid evolves as well. You have this magnetic tension as well as a magnetic pressure, and then you need to come up with some sets of equations for how those magnetic fields will couple to the fluid. These expressions here mean that you have a whole cacophony of other kinds of waves that are going to be present in a plasma that simply are not present in a neutral fluid, which means that your turbulence isn't just going to be your eddies shearing one another, but actually alphenic fluctuations where you have combination of both the density, the magnetic field, and the velocity fluctuations all propagating along or transverse to the local magnetic field. This is a simulation of a particular kind of a particular limit of kinetic theory called gyrokinetics, where we see the actual structure of the current running into each other and moving to smaller and smaller scale structures every time those alphenic fluctuations run into each other. And so that kind of interaction is what replaces these fluid eddies interacting right there. So from there, we need to ask some important questions about how energy is transported through and eventually removed from these systems, right? We have that nice, simple Kolmogorov picture, these arrows going down and down and down in scale space until you eventually reach some spatial scale where viscosity or some other dissipative process will remove energy more quickly than it can cascade to the next scale. That's this nice little red arrow moving down here, or this blue arrow moving down there. The important questions that we're trying to understand are exactly how you have this cascade, what mechanisms are operating it, and how energy is actually removed from this system, right? What mechanisms are actually pulling energy out of the cascade? Importantly, you also are going to have the potential to have non-local transfer. Effectively, these purple arrows here that will, instead of moving from scale L to L over 2 to L over 4, will immediately jump over and move your energy all the way from very large scale to very small scale fluctuations. we have a plethora of different kinds of theories for how these processes should act, but we still do not have sufficient observational confirmation of that. And so one could importantly ask, why is this important? Well, one of the reasons is we'd like to really understand astrophysical objects that we fundamentally will never be able to send a spacecraft to in our lifetime, right? If you look at the observations of Sagittarius A star, they're wonderful results that the Event Horizon Telescope has produced, allowing us to actually visualize the structure around these gargantuan objects. But fundamentally, all we're getting is photons. If we're lucky, we'll get some gravity waves as well. But in order to fully interpret those photons, we need to do the appropriate modeling of the plasma that moves around these different systems. And depending on the assumptions that you build into those models, whether or not you have different kinds of dissipation mechanisms, such as Landau damping or magnetic reconnection, you're going to get fundamentally different interpretations of the spatial structures. That's what this paper by Chael found. By basically putting in different models for how the heating happens, you get fundamentally different descriptions for whether you have a really strong column, a hot column that arises, or if you have a much more broad, hotter disk in comparison. One can work on improving these particular kinds of models. A paper that a grad student of mine published last year, improving that house model. But there's also a lot of other important things other than just understanding Sagittarius A star. Turbulence plays a fundamental role in a variety of different universal plasmas. It seeds where the density clumps in star-forming regions arise. And depending on if you have compressive or solenoidal, two different kinds of turbulent processes, you will get a fundamentally different distribution and a different number of actual stars in a particular star-forming region. It enables angular momentum transport and accretion disks. So for those of you that will eventually work through the MRI calculation, trying to understand how you can actually get mass to fall into the inside of an accretion disk without violating any conservation laws, turbulence is one of the mechanisms that enables that. Additionally, it is something that we see in the interstellar media between all of the different solar systems and stars. And we actually see this so-called great power law in the sky, where that k to the minus 5/3 spectrum is seen across 10 orders of magnitude. So this is clearly a process that happens universally. This is a process that we've studied for a while. And despite some claims in the literature that we've effectively reached the end of the road in understanding this turbulence, there are still a number of open questions trying to understand how energy is dissipated distributed in both time and space, how energy is cascaded through, and what happens when we get to those really, really clumpy features, right? If you remember the movie at the very beginning of the talk, where we saw more and more of these current sheet-like structures forming, we need to understand, are the physical processes that are happening there fundamentally different than the ones that are happening in other locations? So how do we go about doing that? Well, one of the easiest ways to do that, and I put easy in inverted quotes there, is to actually measure the plasma that is naturally produced by the sun, right? It is difficult to make a plasma in a lab. You can wait for lightning to strike you, but we have this continual source of solar wind being output by the sun, filling the entire heliosphere. And because of that, we have this natural laboratory for measuring a whole number of different plasma processes. So this is that fleet chart that NASA will frequently show in terms of the different missions that are filling the heliosphere. As Dan mentioned, missions have a life cycle. And so what you see here are missions that are at a number of different points in their life cycle. So for instance, everything that's in blue are things that have launched and are in their primary mission. Sorry, in green. Everything that's in blue are things that launched a while ago and they've gone through their primary mission, but they're still continuing to provide useful science. And so NASA has continued to operate those missions up there. The things that are in in orange and yellow are missions that are in earlier states of their mission. So they're either in phases B, A or B, so they're in that preliminary stage or in their requirements development. So that's all the yellow ones, or they're in phase C, D, where they're actually building the individual instruments. They're actually integrating them all to the spacecraft, and they're moving them to the rocket to wait patiently for those different rockets to take them to where they're going, in the case of, for instance, Escapade. So we have this whole class of different kinds of missions at different phases that are measuring a number of different processes, either very, very close to the sun or within Earth's own magnetic field. We can use this data to either stare at specific physical processes or to gather, a quarter century worth of data just sitting at the Lagrange 1 point, which is the gravitational null between the Earth and the sun. So the WIND spacecraft has just been sitting there for decades and decades now, and in doing so has gathered up a whole plethora of data that allows us to look for particular times when particular processes are expected to occur. So for instance, plasma beta, who knows what plasma beta is? Who has heard of plasma beta?
I've heard of it, but I don't remember what it stood for.
No worries. This is an educational process. So if you go all the way back to this expression right here, where we have an expression for how the fluid evolves as a function of time, you have this term right here, where if you block out the b squared over 8 pi, that's just the normal thermal pressure that helps support and push along the fluid. This term right here, this b squared over 8 pi, is the magnetic pressure. And what beta is, it's the ratio of those two different things. It's the thermal pressure over the magnetic pressure, which effectively tells you, in this particular system, is the thermal pressure dominant, is the magnetic pressure dominant, or are they kind of an equal partition? And depending on which of those regimes you're in, you're going to expect fundamentally different processes to arise. Is the magnetic field driving the fluid behavior, or is the magnetic field just very weakly located and you're effectively getting mostly just a fluid response with a little field entrained? And so you want to be able to test theories that have dependencies on these kinds of parameters. And in doing so, you'll be able to say, okay, I need to find some plasma where you have really high beta, where the thermal pressure dominates, or you have really low beta, where you have mostly the magnetic field present. Sometimes you need to go to slightly different areas in the solar system. This bottom panel right here is all from 1AU. When you move closer and closer to the sun, the magnetic field becomes stronger and stronger, and so beta drops. Within the magnetosheath, because things become hotter and hotter, you'll see higher plasma betas that are closer to what we expect to see astrophysically. So effectively, by going to different places in the solar system, we can sample these different sorts of environments. This is a nice chart from a paper that was actually just published, I think, last week, where they've lined up all of the heliospheric missions that have gone to different places in the solar system. It looks like they actually don't have wind on here. I'll ping the authors about that, where they're going from Earth and inwards in the case of Orbiter and Parker Solar Probe, or further outwards in the case of Voyager's Pioneer and New Horizon, thus enabling us to get a broad sense of not only how things change as a function of plasma parameters, but also how things change as a function of distance from the sun. So what do we actually measure when we go out there, right? We're not just going to send robots out there to be out there. We want to make sure that they're measuring some quantities that we can compare to the observation, to the theories that we care about. So we fundamentally need them to measure electromagnetic fields, and we need them to measure charged particles. Charged particles, at least in the thermal part of the distribution, can be described in terms of some sort of velocity distribution function. And those are shown here in this set of plots from the Helios spacecraft. Effectively, those are all measuring things that are either very isotropic, things that look like a typical gas in the air that you're breathing right now. But as you get closer and closer to the sun's surface, that's shown as you're going further down on these charts, you get things that are much more significantly elongated transverse to the local field direction, this dashed line, as well as having these secondary beam populations that arise. So we need to be able to understand those kinetic properties of these distributions. We also need to look at how they couple to the local electromagnetic fields that we see, shown, for instance, in this nice spectral distribution. If you want a review of how these measurements are made, section 2 of Verschaar, Klein, Maruka Living Review of Science, that 2019 paper down there, goes into great detail. It's a paper myself and 2 colleagues wrote as a introduction to upper level undergrad and lower level grad for the fundamental things that we want any of our grad students to know about in situ heliophysics. So if you're interested, I would definitely take a look there. There are some limitations, though, on everything I've talked about so far, right? We're looking at this multi-scale disorder. We're looking at these multiple structures that are distributed throughout space. And frequently, we're sending just a single spacecraft up there to make these measurements, which means that you really are not getting a full picture of all of that structure. Typically, what we do is we send that single spacecraft through this nice red line, through this turbulent mess, and then we say, okay, we can convert that time series into a frequency series, and if we assume that we're moving really quickly, so quickly that there's not going to be any evolution in the system itself, we can equate that frequency series with a physical scale. And in doing so, we can test some of those theories that we've produced. However, this is fundamentally limited. And we've known that for some time. As far back as the 1980s, NASA commissioned a Explorer study group that was led by a renowned turbulence theorist, Montgomery, where they stated that the optimal value of n is likely to depend on the kind of problem being studied. Generally speaking, n is 3 is more powerful than 2, and 4 is even better. The point at which increasing n by 1 is not desirable is largely determined by economic considerations. And so we've known that having more than one spacecraft carefully positioned so that you can optimally study the spatial and temporal evolution is something that's necessary to advance our understanding of these systems. We've known that, and both ESA and NASA have launched multi-spacecraft missions before. So missions like Cluster and MMS have launched 4 spacecraft at a time and have carefully designed their orbits so that they'll be sampling at specific spatial scales. For instance, Cluster at some times was focused on ion scales, where things are about an ion gyro radius apart. MMS focused on very small scales, where they're looking mostly at reconnection physics, as well as electron processes that are occurring. Fundamentally, the next step that we need to take, though, is to measure more than one scale at a particular time. And that's what a mission like HelioSwarm is proposing to do, effectively saying we need to have more than 4 spacecraft so that we can simultaneously sample how a plasma changes as it moves from that fluid MHD description through and past the ion kinetic scales, so we can understand what's happening at the end of that cascade that I've pointed to you in that power law distribution several times. So what fundamentally do we need to measure? We've come back to our friend, the induction and momentum equations. Fundamentally, we can, and it will be an exercise left to the reader. I can send you some notes if that would be useful. Simplify this expression by defining this thing that we call the Alsacer variable. Effectively, all we're doing is we're taking the velocity field and we're adding to it the magnetic field, but because you need to have the same units in order to add 2 things, we normalize the magnetic field in such a way that it's written in these velocity units. This gives us these things called Alsacer variables, this z plus or minus, which describe fluctuations moving along or against the local magnetic field direction, and we can understand the individual terms in that expression. But most importantly, almost every single one of the theories that I've hinted at through this talk so far depend on understanding how these Alsacer quantities change as a function of scale, asking the Alsacer field here and the Alsacer field here some distance L apart, how different are they? And when I double L, or when I make L half the size, does that statistical difference persist? Does it become larger or smaller? And how does that change in a statistical fashion? So that tells us that we need to make these measurements across a wide variety of different scales. And so that's what led us to design the specific trajectories that we have for HelioSwarm. So this is a spirograph plot, as the team likes to call it, where we're looking at the position of the HelioSwarm observatory. That's going to be this pentagon right here. It undergoes these 14-day orbits where it gets to within about 10, 15 Earth radii away from the Earth, and then moves out to about 60 Earth radii, about the Earth-Moon distance, before falling back down again. This orbit enables us to make measurements in a number of different environments. Specifically, we can see the pristine solar wind, this red out here, as well as inside the magnetosphere, these different blue lines that you see, and then this foreshock connected region. So areas that are not inside the magnetosphere, but are still connected magnetically because of the Parker spiral that's connecting to the Earth. That's just showing one of the points that the spacecraft is going to be at. The really interesting thing is the fact that we're launching, we have 9 spacecraft here. We have 8 nodes around a central hub. So that central hub is shown here as red, with the 8 nodes shown as these black dots right here. We see those black dots. Some of them are always staying very close to that central hub, while others are going much, much further away. That's going to enable us to see how the plasma nonlinearly reshapes itself over both thousands of kilometers down to hundreds and even tens of kilometers, and making those measurements in the same parcel of plasma so that we can statistically pull that apart. Referencing that life cycle of a mission, HelioSwarm right now is in phase B, which means that we competed for a explorer mission, and NASA put out an announcement of opportunity. We went through several phases of that competition. We were selected for it, and now we are in what is called phase B, where we're finalizing our requirements definitions. Once we have those finalized, we'll put them before a board, and they will say, yea, verily, these make sense for the science that you are looking to do. And then we will start actually bending metal and moving on to phases C and D, and then eventually launch and enter into phase E. Just for a bit of context, this is, I don't know, 1,000 kilometers versus tens of kilometers is sometimes difficult to put in one's head. And so this is just a projection of those larger and smaller loops onto something slightly more familiar in terms of the US, the continental US present here. So based on that rambling about the Alsacer variables we went into earlier, what instruments actually need to be on each of these spacecraft? Well, on every single one of the spacecraft, we have a collection of three instruments: a fluxgate magnetometer, a search coil magnetometer, and a Faraday cup. The 2 magnetometers will allow us to measure the magnetic field over a broad range of frequencies. They each are optimized to look at different frequencies, and we'll then merge them together to get an understanding of the fluctuating magnetic field. And then the Faraday cup will measure the density and the velocity, the vector velocity, at sufficiently high cadences to be integrated in with the magnetic field observations so that we can construct those Alsacer variables. On the central hub, which is a more beefy spacecraft, this ESPA ring over here that has room to put an additional IESA on it, it will give us higher resolution but slightly slower measurements of the ion and alpha density, alpha full velocity distributions. Additionally, Phyllis Whittlesey, who's at SSL, is the lead for a student electron instrument, where she'll be leading a group of students learning how to build, install, and operate a instrument on that central hub as well. The thing that I do want to drive home is that what this mission is going to enable is using all of these measurement points together with 28 instruments spanning multiple different scales will allow us to combine together to do different kinds of analyses that you fundamentally cannot do with a single spacecraft. And so that allows us to look at the different specific goals that we have. For those that are interested in the process, one cannot simply say it would be a cool idea to go out and build this mission, but rather you write what's known as a science traceability matrix, where you say, these are the objectives of the mission. These are the goals of the mission, which are broken up into smaller objectives below it. And then you have to say, these instruments enable us to make progress on these particular objectives. And so in our competitive phases, we decided that these were the specific goals that we wanted to look at, revealing how energy is distributed in turbulence, and then understanding how that turbulence is changed when it runs into large spatial structures, whether it's the magnetosphere or coronal mass ejections that are erupting from the sun's surface. So for those that are interested in that element, I'd be happy to talk more about the actual process of defining these kinds of goals and objectives. But it's also sometimes better to simply simplify these down from the specific words that we used in a report and say, look, we want to understand how turbulence is structured, how it evolves, and how boundaries reshape it. So in order to do that, we have to take advantage of the actual structures that we have in terms of the geometries of the different spacecraft. So fundamentally, the different analysis techniques are either going to take advantage of looking at the difference between two different measurement positions, something we call a baseline separation, or take advantage of the fact when you have 4 different spacecraft, you can make a tetrahedra of that and use that to calculate the gradient of some field quantity that's moving past that spacecraft. If you have 9 spacecraft, that gives you 36 different baselines. It also gives you 128 different tetrahedra that you can choose from, and more generally, 382 polyhedra with at least 4 vertices, which will enable you to do the specific kinds of analysis techniques that we want to perform here. So if you're interested, the actual Phase B representative trajectories are available on this Zenodo website. That's available right there. I can also send it out if you're interested. So if you want to run these trajectories through your favorite simulation, maybe something you're looking at for your REU, those have been made publicly available so we can better engage the heliophysics community on that. So what are the actual characteristics and what are the kinds of analyses that we need to perform? Well, the first of them is going to be that baseline separation, right? So the differences between the different spacecraft that we're looking at, that enables us to have to actually look at those 2-point structure, 2-point correlations, the differences that between any 2 spacecraft, and also calculate things like the cascade rate, the actual rate of energy transfer as a function of time. And so what you see here is just a visualization of those very large baselines and simultaneously those very small baselines near that central hub, allowing us to look at the change in the plasma as a function of scale. Importantly, we want to actually quantify that because we have to hand our flight dynamicists a specific set of requirements. And that's something where we're saying, look, we need to make sure that we have separations in 3 different orthogonal directions. And we need to make sure that they span the 3 different physical scales that we care about, the MHD, the transition, and the kinetic scale. And so here is how we actually score ourselves and tell us that, yes, we are in the right region. So when you're in these nice solid lines out here, we have one of those 36 baselines at each of the different scales at each of the 3 different directions, enabling us to look at the full 3-dimensional setup of the turbulent structure. But we also fundamentally need to understand how the underlying fluid fields change, right? We need to look at the gradients, and that requires having good that requires us having good tetrahedra. And so here's an example of the different kinds of tetrahedra that we can make, basically seeing one that's very, very large. Actually, it's showing us 2 that are very large, both the green and the blue lines. And then you'll see this very small inner one down there, which is going to allow us to look at the changes on very, very small structures. And so that allows us to apply a whole set of different gradient approaches to the system. So this enables, in order to apply these gradient methods well, you can't have something that's a complete pancake or a sausage, right? That's not going to give us a good ability to look at the gradient over these different fields. And so we need to make sure that, mathematically speaking, the elongation and the planarity are relatively small. And so in doing so, we can look at the 382 different polyhedra that we have and say we need to make sure that the polyhedra are regular enough and well separated in their various sizes, so we can look at the gradients on both small scales and large scales simultaneously. So this enables us to do a whole plethora of different kinds of calculations, basically trying to understand, okay, can we reconstruct the local magnetic field? This is work that my former grad student, Teddy Baronin, was doing, looking at saying, look, we have these 9 different time series moving through a plasma. How accurately can we reconstruct the underlying turbulent fields, right? It's not a nice, simple laminar flow. And he found different methods, things like a radial basis function or a combination of an asynchronous measurement with a high cadence measurement in the time direction with a sparse radial basis function in the transverse direction, led to superior representations of the underlying fields. And so there's a lot of really interesting ongoing mathematical work that needs to be developed in order to fully take advantage of this, what will be a very large data set that we're working on producing. And so I think I was told to prepare for about 40 minutes, and so I will try to not talk beyond that. But this gives us a multi-point, multi-scale observatory that is going to allow us to reveal how energy moves through and is eventually removed from turbulent plasmas throughout the universe. So there's a lot more details in this Space Science Review article on the left. And again, if you're interested in using these trajectories yourself, you can see them, get them at that Zenodo link on the right. So with that, I'll pause for any questions that any of you may have. Thank you for your attention.
That was just fantastic. Thank you, Chris. Learning so much more that I didn't know previous to this. Really appreciate that. Hopefully we'll have some good questions here. But just really quickly to make sure that I fully understand, these spacecraft are going to be put into orbits to get these tetrahedrons, and not, there's not continuous maneuvers throughout the mission. Is that correct?
There will be about 2 maneuvers per orbit in order to keep us in a precise station keeping, but then the rest of the time is just Newtonian or orbiting. So our flight dynamicists have worked out how to inject us, which is in theory what's showing right now, into the science orbits. And then once we're in that orbit, the hub will start deploying the nodes on a pair basis, so deploying 2 at a time each orbit. And at which point in time, the hub is free floating, and we'll add little bits of delta V to the nodes every orbit to make sure they stay in this precise set of trajectories we want.
Okay, and are these trajectories pretty much already figured out, or are you still contributing to mission design at this stage as far as your
contributing to mission design? We have a whole hexadecimal setup of different possibilities in terms of, okay, this specific spacecraft, can we adjust the shape of this node so we may lose a few baseline hours but get more polyhedral hours as they contribute at different phases of the mission. The other thing that you have to worry about is things don't always work in space. And so if node 2, which is part of the inner tetrahedra, stops functioning for some reason, can we replace its operation by moving or adjusting the orbit of one of the other nodes? And in fact, we have books of plans that aren't actually books. They're spreadsheets of plans of saying we can move node 3 from loop 3 into loop 2.4 in order to fulfill some of that. And so we are continuously going through these processes of getting better orbits and of optimizing how we will use the nodes if a redundant need is necessary. So yeah.
Got it. Okay. Yeah. I'm actually helping out with the ICON mission, and we had just proposed an extended phase E for 5 years, which back in the day was kind of automatic.
Yeah.
We lost touch with the spacecraft, and there's no backup. You guys have backup capabilities here too.
Exactly. And so but it's a massive phase space in terms of trying to understand, okay, if I move this node over, what happens to that geometry? So it's something that I've written a Monte Carlo setup so that we can say, okay, we have this likelihood of a safe mode each hour, and then accumulating how many hours are we predicting to accumulate, at least on a statistical basis, with this level of
safe mode or that level of safe mode. So yeah.
Okay. A question about the sun's magnetism. So when say a CME goes out from the sun, or
Yeah.
the solar wind and the plasma, it's always carrying a bit of the sun's magnetism, right? There's always magnetism with plasma, whatever form it's taking as it moves out through space, right?
Yeah.
But the magnetic fields, are they always just extensions from the sun, i.e., they're still connected, so to speak? Or
Yes.
okay, so you're not getting magnetic loops that also, unless it's going
Not at these distances, right?
Yeah.
I saw you had a Parker talk a few weeks back. When you are that close in, you are sometimes seeing bidirectional sprawl, which is indicative that you're close enough that you actually have electrons running in both directions and still being connected down to the surface. By the time you're at 1 AU, you're not seeing that. Now,
okay.
we will be, okay, I'm not an electron person. I stick with the heavy, majestic ions that are much easier and much less wiggly. So we may need to check me on the lack of bidirectional straw at 1 AU. But when we are in the magnetosphere, there actually, think I have a better slide for this. When we're in the magnetosphere, we're not going to be measuring the pure plasma and the pure magnetism that was generated from the sun, but rather we're going to be entering into the region where we are magnetically dominated by the Earth's magnetic field. And so that's one of the fundamental things we want to understand is how does turbulence change as we move from one environment into the other environment.
Okay, fascinating. Wonderful. All right. Well, students, any questions from the audience here or from other members of the team?
This is less so a question, but could you just go back to the slide where you had the paper that you wrote about like the in situ observations? I didn't
Yeah.
get a chance to take a picture of it and wanted to reference it for later. Thank you.
Got it. Yeah, it is. It's going to take me longer to find it. Here we go. So this is Rashawn Klein Maruka Living Review of Solar Physics 2019.
Thank you so much.
Certainly.
So, as far as you're concerned, are there reviews coming up that you need to definitely pass?
Yes. Yeah. So we are currently going through the instrument preliminary design review. So I was in England and France last week, where they presented their designs for a board saying, this is how we will satisfy the requirements that have been handed to us by the project in terms of making sure that we measure. Do I have the cadence plot in here? Right. So we want to make sure that we are measuring at a particular cadence with sufficient sensitivity and over the right span of physical parameters. Right. The solar wind moves at a variety of different speeds. We need to make sure we measure both slow and fast speeds. And so we've now gone through that instrument review for the flux gate and the search coil magnetometer and the ion electrostatic analyzer. We will be going through that review for the Faraday Cup, I believe, coming up in August. Other elements of the engineering team are going through that PDR exercise, and we are moving towards a preliminary design review either at the end of this year or into next year for the entire mission that will then allow us to move from phase B into phase C.
Okay.
Yeah.
And, compared to, here at SSL, we got fairly well known for the Themis mission, which was 5 identical spacecraft.
Yes. Yeah.
Escapade, I think, is
2. Yep.
Barely. I think, they're actually identical spacecraft. I get the feeling here that they're not identical.
Oh, they're very identical. We're trying to.
Oh, okay.
We're trying to push these off a manufacturing line, right? So these 3 instruments right here will all be connected to the same IDPU, which will enable them to basically be controlled in the same way whether they are on the smaller spacecraft or the larger spacecraft. So there will be 8 identical nodes, as we call them, and then one hub that is a distinct kind of spacecraft. And so 8 of them will be identical. We hope to have low non-recurring costs so that we can afford to pay for 9 of these spacecraft total. So yeah.
Okay, okay. Sorry, I missed that. Yeah. All right. Anybody there else? Questions or
Just
opportunity?
wondering, yeah. You said that the like magnetic pressure increases as the temperature increases. Is that because like the magnetic pressure maybe causes that temperature increase, or what? Like, how does this happen?
So there are 2 different contributions to that plasma beta. One is just the strength of the magnetic field, and therefore the magnetic pressure is going to be B squared, will scale like B squared. Then you have units, some terms to make sure that you're in pressure units. That is distinct from the thermal pressure, which is associated with just how hot the system is and how dense the system is. And so as you go into the magnetosheath, you enter into an environment where the plasma is hotter. And therefore, compared to the strength of the magnetic pressure, your beta goes to a higher value. And so that's similar to where you're in an astrophysical system, or even if it's a bit cooler in terms of Kelvin, the magnetic field is much weaker, and so therefore the thermal motion will dominate, and you can describe it dimensionlessly as effectively the same kind of plasma. And it's that kind of de-dimensionalization game that theorists will play to say, I can't fly all the way out there, but if I can measure that here in the laboratory, if I can measure that up in space, I can get a sense of the underlying processes that are happening in both places.
Thank you.
All right. Anyone else? Well, Chris, thank you so much for your time. This was absolutely fascinating. I'm going to
Certainly,
rewatch
yeah.
it a few times because, oh, Kamal, you have a question here.
Hi, yeah, sorry, my Zoom was being a little silly. Yeah, I was wondering for people who are like interested in this seems very like technical on the CS side, what skills people should be working on picking up to be able to advance to doing something like this in the future.
You mean CS as in computer science?
Yeah.
Okay.
So I think there are a number of skills that are very important for handling this volume of data, right? Making sure that you have a understanding of how to perform the necessary mathematical operations in an efficient fashion. So my grad student Teddy was actually an applied math PhD. And so what the focus of his work was doing was identifying what are the kinds of mathematical manipulations that will be useful for a volume that is rich as this, and then determining what's the best way to actually implement that within a framework that will allow us to do this for, a whole year worth of data. And so I think making sure that you have familiarity with the underlying mathematics, that you have a familiarity with the underlying plasma processes, and then making sure that you, in your language of choice, are able to work with these large sorts of data sets. Almost everything that NASA produces is in a CDF format. Have you guys talked about CDF? Okay, so it's a unique format that is not used in all the other fields. Sometimes they use HDF5s, right, to compress these large volumes of data and something you can hand over to other people on the internet. And so learning how to work with that kind of data is probably the best thing that you can do. So, if you want to learn how to play with this, grab some magnetic field data from Parker Solar Probe, try to calculate a Fourier transform on it, see if it looks like a spectrum that makes sense, and then just work by doing with the kind of data that already exists.
Are you, I mean, in this case in particular, I guess I would say all the NASA missions, but certainly ones that I've been associated with, there are always outside researchers just waiting for the data, and they're
Yep.
just, new publications are coming all the time, even though they
Yeah.
were part of the mission team. is that a real hope here that
Oh yeah, yeah.
that,
There's going to be a 3-month calibration period because dealing with 28 different instruments, making sure that all the offsets are set correctly.
Mhm.
And then all of the data is going to be released on CETA in the same way that all other NASA missions are. We are committed to open science. The Science Operating Center is currently working on building Python packages to help people actually load and visualize this volume of data. And so we are very committed. We are a small science team. There's only so much science we can do, and it's going to be better if we take this data and hand it to the community so more people can engage with it. So yes, this is not something we will sit on for a year and then eventually just, hand off when we're bored with it. We want active participation from the community.
Right, right. Yeah. I mean, so many researchers kind of just they're not mission design people. They don't get on mission teams too often, but they do
Yeah.
sit and wait for data to arrive.
Yes. Yeah. Yeah.
Whether they're, a Mars expert or a Helio, yeah, they're waiting for these missions to happen, even though they may not be part of the team. Yeah, always kind of forgotten about that other piece of the pie that, these missions to provide extraordinary amounts of data that kind of just keep the machinery going here, and new things come around, even though it's maybe not the mission team who made that particular finding.
Exactly. Yeah. No. And sometimes having a new set of eyes is a good thing to look at the data in a different way. So
Definitely. All right. Well, with that, again, we thank you so much. This has been a real honor for us, and we're so glad to have you here, Chris. Thank you. We hope to
certainly,
hear more about HelioSwarm in the news, hopefully soon.
certainly. Yeah. Yeah. No, we're all looking forward to continuing pushing forward. So yeah.
Okay.
How
What should we
long
be
do you
looking for
think?
next, date-wise?
Preliminary design review will be at the end of this year or sometime into next year, depending on the budget situation.
Right.
And so the moving into phase CD will be the next big milestone that we're moving towards. So,
Yeah.
yep.
Okay. Fingers crossed for that. All
Yep.
right. Thank you.